vulnerabilities. This video is pretty much a brain dump of everything that I consider to be fundamental knowledge when it comes to SQL injection attacks, and so it's going to be a long one. So if you're only interested in a specific topic related to SQL injection, then I would recommend going to the description and checking out the timestamps that I have mapped out to the different topics that I cover in this video. Okay, let's get started. We'll start off with describing what a SQL injection vulnerability is and the technical details behind this category of vulnerabilities. So in this section, we'll discuss topics like what are SQL injection vulnerabilities, what are the different types of SQL injection vulnerabilities, how common are SQL injection vulnerabilities, and so on. Next, we'll cover how to find SQL injection vulnerabilities from both a black box and a white box perspective. So if you're given an application and possibly even the source code of the application, how would you approach testing the application in order to determine if it's vulnerable to SQL injection? In the third section, we'll cover how to exploit SQL injection vulnerabilities. So imagine you're testing an application and you discover that one of the input vectors or one of the parameters is potentially vulnerable to SQL injection. In that case, how do you go about exploiting that vulnerability in order to gain access to sensitive information or even potentially gain remote code execution on the server? Last but not least, now that you have successfully found and exploited a SQL injection vulnerability, what recommendations can you give to the client in order to remediate the vulnerabilities that you found? So in this section, we'll cover the different techniques that you can use to prevent SQL injection vulnerabilities. Okay, let's start off with the first section. What is SQL injection? SQL injection is a vulnerability that consists of an attacker interfering with the SQL queries that an application makes to the backend database. So if you as an attacker can manage to interact and change the SQL query by adding SQL characters or SQL code in an input vector of an application, then the application is definitely vulnerable to SQL injection. Now, to better understand this, let's take an example. Imagine you have an attacker, a web server, and a database. The application that the web server hosts has an authentication functionality where the user has to put in their username and password. And once the username and password are put in, a query is made to the database to see if this username and password are in the database. And if they are, then the user is presented with his or her profile page. If the user enters an incorrect username or password, then the user is presented with an error message that says you have entered an incorrect username or password. So in this case, we clearly have two input vectors, the username field and the password field, that talk to the backend database. So they get included in a query in the backend database. And so we definitely need to test these input vectors for a SQL injection vulnerability to see if that input is validated in any way. So let's see what an attacker can do. In this case, what an attacker is doing is in the username field, instead of just adding a username, the attacker adds the username admin, the account that the attacker wants to compromise. But then the attacker also adds some SQL characters after the username. So a single quote and then a double dash, which stands for a comment. So what happens is that this username gets included in a query. So what the query does at the backend is it says select star from users. So select all the entries from the users table where username is equal to whatever username is put in here and password is equal to whatever password is put in here. Now, if this input is properly validated, and we'll talk about that in the next couple of sections, if this input is properly validated, then the database will literally look for a username that is equal to admin code dash in the database. And it won't find one because no one has that username. And so the attacker would be presented with an incorrect username or password. However, if this application is vulnerable to SQL injection, so it doesn't use parameterized queries, it doesn't validate user input, then what will happen is that any SQL characters or SQL code that the attacker adds as part of the payload will become part of the query. And so in this case, what's happening is select star from users. So select the entries from the users table where username is equal to admin, the single quote over here that the attacker included closes the string for the username, and then the double dash stands for a comment, and so it says comment out the rest of the query. And so what happens is the query becomes this. So select all the entries from the users table where username is equal to admin. Now admin is an existing username in the database. And so what happens is that the database will return the admin user profile, and the attacker gets logged in as the admin user. So essentially what happened over here is that the attacker exploited a SQL injection vulnerability in the login functionality of the application in order to bypass authentication. So in this case, the attacker no longer needed to know the admin's password because the attacker was able to change the query to no longer ask for the admin's password. So that's one example of how you could use SQL injection vulnerabilities in order to bypass authentication on login functionality. Now, let's talk about what are other impacts of SQL injection attacks. And the real answer to this is that it really depends on the context of the SQL injection that you're exploiting. So some SQL injection vulnerabilities will only allow you to view data, whereas others will allow you to actually modify data. So when I was coming up with this slide, instead of listing the infinite number of things that you could do to applications with SQL injection vulnerabilities, I instead decided to just compare it to the SIA triad, so how it affects confidentiality, integrity, and availability. So in terms of confidentiality, some SQL injection vulnerabilities will allow you to view sensitive information, such as usernames and passwords, so the application's username and password. And that's an example of how you impact the confidentiality of an application by accessing information that you shouldn't have access to. In terms of integrity, some SQL injection vulnerabilities will allow you to alter data in a database. And an example of that that I exploited not too long ago is an application that allows you to update an email address. And so because this was vulnerable to SQL injection, I was able to update another user's email address to one that I control. And so what I did is, because I control this email address, I reset the password of the user, and the reset token was sent to the email address that I own. And so I hijacked the user's account. And that's an example of how to affect the integrity of the application, because you were able to alter data that you shouldn't have otherwise been able to alter. It also affected the availability of the application, because I denied, when I reset the user's password, I denied access to the user's account. And so I affected the availability of the application. And of course, in certain scenarios, SQL injections could actually lead to remote code execution on the operating system, and that affects confidentiality, integrity, and availability all at once. And you would gain access to the operating system with the same privilege that the database is running with. And so you got to be very careful in terms of making sure that the database runs with the least privilege possible. And we'll discuss that in the last section when we're talking about things like defense in depth and how to prevent SQL injection vulnerabilities. Okay, so we talked about the impact of SQL injection vulnerabilities. Now the question is, how common and how critical are SQL injection vulnerabilities? And one way to measure that, and it's not bulletproof, is the OWASP Top 10 list. So for those of you that have never heard of the OWASP Top 10 project, it's essentially the list of top 10 most critical security risks to web applications. It's updated every couple of years. So you could see over here, I've got the 2010 list, the 2013 list, and then the 2017 list. I believe 2020 is in the works, so I think it was submitted but has not been approved yet, but I could be wrong. So I think 2017 is the latest one that we have right now. And you'll notice over here it does change across the years. So you've got cross-site scripting was the second most critical risk to web applications in 2010, and then it became the third most critical risk in 2013. And then it dropped all the way to the seventh most critical risk in 2017. And you'll see some of them completely disappear. So insufficient transport layer protection was number 9 of most critical risks in 2010. but it completely disappeared in 2013 and 2017, and that's probably because it's so easy to now get certificates and use HTTPS on your site. Even malicious sites use HTTPS right now, so it's definitely not a risk anymore. But then you see also new ones get added. So for example, insecure deserialization over here was never a risk in 2010 or 2013, was not part of the list, and in 2017 it became part of the list. Now for SQL injection vulnerabilities, they fall under the first most critical risk to web applications. So they fall under the injection category. However, it's worth mentioning that this covers all of injection vulnerabilities, not just SQL injection vulnerabilities. In fact, the likelihood of SQL injection vulnerabilities existing in applications has decreased across the years for many reasons, and we'll discuss that in the last section when we discuss how to prevent SQL injection vulnerabilities. Nevertheless, it is still a critical risk because, as we saw in the past couple of slides, if you do have even just one parameter that is vulnerable to SQL injection, it could potentially lead to remote code execution on the server, so a full compromise of the underlying server. All right, so in the past couple of slides, we got a high-level overview of what SQL injection vulnerabilities are. Now we're going to go at a more granular level and talk about the different types of SQL injection. SQL injection vulnerabilities can be classified into three major categories. The first is in-band or classic SQL injection. The second is inferential or blind SQL injection. And the third is out-of-band SQL injection. Now, in-band, or also known as classic SQL injection vulnerabilities, are ones where the attacker uses the same communication channel to both launch the attack and gather the results of the attack. If that doesn't make much sense to you, that's okay, don't worry. I actually have a couple of slides explaining each type in detail. Right now, I'm simply giving you a high-level overview of what each type is. Now, in-band or classic SQL injection is divided into two types: error-based SQL injection and union-based SQL injection. Error-based SQL injection is a technique where you force the database to generate an error, giving you more information about how things operate at the backend. So an example would be if you have a parameter that is vulnerable to SQL injection, and then you put into that parameter a single quote, and that breaks the backend query, which generates an error at the application level. And so what happens is that the error tells you things like the version of the database, so the type of database that they're using at the backend, the version of the database, and sometimes the error will also tell you the exact SQL query that is being used at the backend. And this would make your life so much easier because if you know the exact query, you don't have to guess it using trial and error. And this way you could just build your SQL payload. So that's an example of error-based SQL injection. For union-based SQL injection, it's a technique that leverages the union operator to combine the results of two queries into a single result set. So in this technique, you don't just output the result of the original query that the application makes, but you also output the result of a query of your choosing. And of course, something that you would be interested in is, for example, the usernames and passwords of the users of the application. So you would use the union operator to output the credentials of the users of the application. And again, we'll see examples of that in the next coming slides. The next category, which is inferential, or also known as blind SQL injection. In this type of vulnerability, there's no actual transfer of data via the web application, so you don't see the results in the application itself. Instead, you're stuck asking the application true or false questions, which is what Boolean-based SQL injection is, or causing the database to pause for a specified period of time, which is time-based SQL injection, in order to determine if what you're asking the application is correct or not. Obviously, the way you exploit blind SQL injections is more difficult than classic SQL injections. However, the impact, even if you're not seeing the results right away in your application, the impact of exploiting the vulnerability is still as bad as in-band or classic SQL injection. And we'll see examples of that in a bit. Okay, the third and last category is out-of-band SQL injection. This occurs when the attacker is unable to use the same channel to launch the attack and gather the results of the attack. It usually relies on the ability of an application to make a network connection, so for example, a DNS or HTTP request to deliver data to an attacker. I've seen people loop this type of SQL injection under inferential or blind SQL injection, which is a fair thing to do. However, if you look at resources online, most of the resources out there will separate them into 3 different categories, and that's why I decided to also separate them into 3 different categories in my video. Okay, let's go more in depth about each type, starting with in-band or classic SQL injection. We talked about in-band SQL injection vulnerabilities occurring when the attacker is able to use the same communication channel to both launch an attack and gather the results of an attack. So to put this in plain, simple English, if you exploit a SQL injection vulnerability by sending a SQL payload in one of the fields of an application, and then you see the result of your SQL payload presented directly to you in the application, then this falls under the category of in-band SQL injection. Now, just by the nature of how this specific type of vulnerability works, it's much easier to exploit than other categories of vulnerabilities. And the reason behind that is because you actually see the result of your attack in the response of the application versus having to infer the result like you would have to in blind SQL injection. Again, we said that there's 2 types of in-band SQL injection, error-based SQL injection and union-based SQL injection. And we'll start off with error-based SQL injection. Error-based SQL injection is an in-band SQL injection technique that forces the database to generate an error, giving the attacker information that could potentially aid in developing the injection payload. So let's take an example. Imagine you have an application, www.random.com, that has an ID parameter that is vulnerable to SQL injection. In this case, we're putting a single quote in the ID field, and because that is a SQL character and this is vulnerable to SQL injection, that single quote will become a part of the query, and so it'll break the backend query and it'll output an error. And an example error is you have an error in your SQL syntax, check the manual that corresponds to your MySQL server version, blah, blah, blah. So in this case, it tells you that you're using MySQL. That's good information to know. It might also tell you the version. And again, in certain scenarios, the error might also give you the query that happens when you put an ID parameter. So what's happening when you put, for example, an integer in the ID parameter, the exact query that happens at the backend. And this way, if you have the exact query, it's so much easier for you to develop your payload versus sending a bunch of requests to the application in order to determine what the payload is. And so this is in-band SQL injection or classic SQL injection because you see the output of your SQL injection right there in the application. And it's error-based because the idea is that you output an error in the application. Next, we have union-based SQL injection. Union-based SQL injection is a type of in-band SQL injection technique that uses the union SQL operator to combine the results of 2 queries into a single result set. Again, I mentioned in the previous couple of slides that I don't want to output just the result of the original query. I want to output a query of my choosing. And if an application is vulnerable to union-based SQL injection, then I get the ability to output the result of a query of my choosing and combine it with the original query that the application is, with the result of the original query that the application is making. Let's take an example. You have your application, www.random.com. It has an ID field that is vulnerable to union-based SQL injection. And if you put in a valid ID, then the page will display all the products that are associated to that ID. Now, instead of just displaying the products associated to a specific ID, I want to output the results of another query. And in this case, the query is select the username and the password from the users table. So output all the usernames and passwords from the users table and then comment out the rest of the query. So in this case, it will output the results of this query over here. We didn't put an ID in, so that would be empty. And then it'll combine it with the results of this query over here, which is the username, so Carlos, an administrator, and the passwords of the users in the users table. Now, of course, the union operator has certain conditions for it to work, and so it's not as simple as, hey, I'm going to output whatever I want in as many fields as I want. It's not the case. Instead, there are certain conditions that you have to follow, and we'll discuss that in the exploitation section of this video. Okay, so that covers in-band or classic SQL injection. Next, let's talk about inferential or blind SQL injection. Inferential or blind SQL injection is a SQL injection vulnerability where there's no actual transfer of data via the web application. So unlike in-band SQL injection, where we directly saw the output of the SQL injection displayed for us in the application, in the case of blind SQL injection, the database does not output data to the web page. And so this forces the attacker to steal data by asking the database a series of true and false questions, and then determining based on how the application responds, whether the application responded with, yes, this is a true statement versus no, this is not a true statement. And again, this will become more clear once we discuss the different types of blind SQL injection and we take examples. Now, just because an attacker can't directly display data from the database, that doesn't mean that this is a harmless vulnerability. Like I said in the previous slides, in fact, it's just as dangerous as in-band SQL injection because you can extract information from the database by asking true and false questions. It's just that this type of vulnerability takes a little bit longer and a little bit more skill set in order to exploit. Okay, and we said there are two types of blind SQL injection, Boolean-based SQL injection and time-based SQL injection. Let's talk about Boolean-based SQL injection. Boolean-based SQL injection is a blind SQL injection technique that uses Boolean conditions to return a different result set depending on whether the query returns true or a false result. So in simple English, again, the attacker sends different SQL payloads that ask the database true and false questions, and depending on how the database responds, then you could infer whether the application responded with true or false. This is sometimes referred to as content-based blind SQL injection, so you'll see those two terms used interchangeably. Now, let's take an example so that this becomes a little bit more clearer. Imagine, again, you have an application, www.random.com, and it has an ID parameter that is vulnerable to blind SQL injection. And imagine in this case, you can't simply use the union operator to output data in the database like we did with union-based SQL injection. So in this case, what you can try to test if the field is vulnerable to SQL injection is first inject it with a false payload. So force a payload that you know is false, and then see how the application responds, and then force a payload that you know is true, and see how the application responds. And if the application responds differently in the false payload versus the true payload, then this is vulnerable to Boolean-based blind SQL injection. So let's take the backend query. So imagine over here, when you enter an ID number, this is the query that happens at the backend. So select the title from the product table where ID is equal to 1. And because ID is equal to 1 is a valid ID in the table, the application will display the title of the products that are associated to ID 1. Now, if we want to force a false payload, what we can do is we could use a conditional statement and 1 is equal to 2. So the backend query would be select the title from the product table where ID is equal to 1 and 1 is equal to 2. Now we said ID is equal to 1 is a valid ID, and so this will evaluate to true, and 1 is equal to 2 will evaluate to false because 1 will never be equal to 2. And so because this is an AND statement over here, you're using the AND operator, they both have to be true in order for the entire where clause to evaluate to true. So this evaluates to true, this evaluates to false. True and false is equal to false. And so the entire where condition evaluates to false. And so it won't display a title from the product table. So in this case, if you force a false statement, you won't get the title of the products that are associated to ID is equal to 1. Now let's see what happens when you force a true statement. So we'll use conditional statements and we'll say ID is equal to 1 and 1 is equal to 1. Now we said ID is equal to 1 evaluates to true because this is a valid ID in the table, and 1 is equal to 1. 1 will always be equal to 1, and so this will always evaluate to true. True and true evaluates to true, and so the where clause evaluates to true, and so the title of the products that are associated to ID 1 will be outputted on the page. And so right now, I have two different responses depending on whether I force a false statement versus a true statement. And so I'm able to tell when the application is telling me, yes, this is a true statement versus no, this is not a true statement. And so now you might be wondering, well, it's nice that I can play around with the application and get it to output true or false, but how does that actually matter? And how does that help me in exploiting a SQL injection vulnerability to get sensitive information from the database? To answer that, let's take another use case. So imagine the same application. The application has a login functionality, and so it has a users table in the database, and the users table has the usernames of the users of the application, so in this case, administrator, and the hashed passwords of the users in the application. And so I want to extract this hashed password for the administrator, but I can't simply output it on the page like I would for union-based SQL injection. And so I have to use my Boolean-based SQL injection in order to output it. And that's only done by asking the application true and false questions. And so the way I'm going to do that is by using this payload over here, which generates this query over here. So you've got, I'll use the substring function, and what that function does, it extracts some characters from a string. So the first parameter that it takes is the string that you want to extract from. The second parameter that it takes is the start position for the extraction, and the third parameter that it takes is the number of characters to extract. So in this case, I'm saying that string to extract from is the output of this query. So select the password from the users table where username is equal to administrator. This query will output this hashed string over here. And then I'm asking it extract the first character in the string and only one character. And so it will extract the first character over here of the hashed password. And then I'm asking it, is this first character equal to S? In this case, the first character is not equal to S because the first character is E. And so this statement over here evaluates to false. True and false evaluates to false. And so the where clause evaluates to false, and you shouldn't see a title from the products page. And so nothing is returned on the page. That means it returned false. That means I know that S is not a first character in the hashed password. Now, imagine I keep looping through the characters and I get to E, and I ask it again, is the first character of the hashed password equal to E? That evaluates to true, right? So the backend query would be true and true. So the entire where clause evaluates to true, and so the title of the products that are associated to ID 1 are returned on the page. And this gives me an indication that it returned true, which again tells me that E is the first character of the hashed password. And so right now you should get an indication of how you're going to extract information from the database and why I said it takes more skill set and more time than union-based injection. And that's because you're asking the application true and false questions, and you're going to have to do that for each character. So you start off with the first character, you loop through all the alphanumeric characters until you get a true result. Once you get a true result, that means you know you discovered what the character is, which is E over here. And then you move on to the next one. And then you loop through the alphanumeric characters until you get another true statement. And then that means you discovered what this character is. And then again, you loop through all the alphanumeric characters until you discover what this character is, and so on until you output the entire string of the hashed password. And this could take thousands of requests. Obviously, you can't do it manually, and so you have to automate the task. And we'll do that in one of the videos where we use Burp Intruder to automate it. We'll also write a Python script that does it for you. And it might seem like it's something that is very difficult, but it's not. Writing the script in Python takes about 5 minutes, 5 to 10 minutes max. And then outputting the string is going to take less than 1 minute, outputting the entire hashed password. So that's Boolean-based blind SQL injection. Next, let's talk about time-based blind SQL injection. Time-based SQL injection is a blind-based SQL injection technique that relies on the database pausing for a specified amount of time, then returning the results indicating a successful SQL query execution. So just like we did for Boolean-based SQL injection, what we do for time-based SQL injection is we inject a payload in the parameter that is vulnerable. And what that payload does, it pauses the application, the response of the application for a certain period of time. So in PostgreSQL, you would use the pgsleep command and input a certain number of seconds. So if I use pgsleep 10, that means I ask the application to sleep for 10 seconds. And so if the response time takes 10 seconds to get back to me, then I know it's vulnerable to time-based SQL injection. If it doesn't take 10 seconds, so it takes the general 1 second to get back to me, then it's not vulnerable to time-based SQL injection. And the example is the same for Boolean-based SQL injection. The way you would extract information from the database is by asking the application true and false questions, except the condition over here is not a response in the application. The indication of whether it's true or false is going to be based on the response time of the application. And so I'm going to say if the first character of the administrator's hashed password is an A, then wait for 10 seconds. And if the response time takes 10 seconds to respond to me, then the first letter is A. If it doesn't take 10 seconds, then the first letter is not A. And again, this can't be done manually. You're going to have to script it, and you can do that in Python where you measure the response time. And then depending on what the response time is, you determine whether it's true or false. Okay, last but not least, let's talk about out-of-band SQL injection. Out-of-band SQL injection is a vulnerability that consists of triggering an out-of-band network connection to a system that you control. So this technique is usually used when you can't apply any of the other techniques that we learned about so far. And it's not a common technique because it does rely on certain features being enabled in the database for it to actually make that network connection. Now, to exploit this vulnerability, you could use a variety of protocols, but you'll see that the most commonly used ones are DNS and HTTP. And one that we will look at in the videos, it's in the Web Security Academy. So in the upcoming videos where we gain hands-on experience doing this, is this example over here, where you exploit the vulnerability by using the xpdir tree stored procedure in MS SQL to perform a lookup of this domain over here. So this domain was generated using Burp Collaborator, and so you own it. Since this is the domain that you control, you can confirm if there were any DNS lookups. If there was, then this is vulnerable to out-of-band SQL injection. And if it's not vulnerable, then you won't see the DNS lookup. We'll see how to do this in the lab videos. Now, once you've confirmed that you have an out-of-band SQL injection, in some cases, you might be able to directly exfiltrate data, whereas in other cases, you might have to use conditional statements like we did with Boolean and time-based SQL injection, where if you do get a DNS lookup, then yes, this is a true scenario. If you don't get a DNS lookup, then no, it's not a true scenario. All right, in the past couple of slides, we discussed the different types of SQL injection vulnerabilities. Now in this section, we'll discuss how to find SQL injection vulnerabilities. So imagine you've been given an application and asked to test it. How would you go about testing the application to see if it's vulnerable to any SQL injection vulnerabilities? Before we cover that, it's worth mentioning that the methodology used for finding SQL injection vulnerabilities differs from one person to another person, and it's usually developed by experience. So just because I give you my methodology doesn't mean that you have to follow it to the letter. Instead, I would recommend that you take what is useful for you from it and then build and add on to your own methodology as you gain more and more experience in pen testing web applications. And that statement applies for finding all the vulnerabilities, not just SQL injection vulnerabilities. Okay, so finding SQL injection vulnerabilities, I've decided to split this into two categories depending on the perspective of testing. And the two categories are black box testing and white box testing. For those of you that have never heard of these terms before, black box web application pen testing is when the tester is given little to no information about the system. Usually the only information that the tester has access to is the URL of the application and the scope of the engagement. So this is similar to mimicking an external attacker that is trying to attack your system. The attacker usually doesn't know anything about the application other than the main URL of the application. Now for white box web application pen testing, it's the complete opposite. The tester would be given complete access to the system, including access to the source code of the application. Now there's a third category that I haven't included on the slide, and it's called gray box web application pen testing. This is a combination of white box and black box pen testing where the tester is given limited information and access to the system. For example, instead of just giving the tester a URL of the application, like you would with black box pen testing, the tester is also given accounts to the application. So when it comes to my methodology of finding SQL injection vulnerabilities, I loop both gray box and black box pen testing into one category, and that's because my methodology is the same regardless of the category. The way I see it is if I'm approaching it from a black box perspective, my scope will be much more limited than the gray box perspective unless I find authentication bypass vulnerability. Nevertheless, the methodology is still the same for finding SQL injection vulnerabilities, whether I'm doing it in public or an authentication page. And that's why they're looped in together. Now, when it comes to white box pen testing, that's a whole different methodology because you actually gain access to the source code of the application. And reviewing source code is a whole different realm than approaching an application from the outside. All right, let's start off by talking about how to test applications from a black box perspective. The first thing that I do when testing an application is map the application. And what that means is I literally visit the URL of the application. I walk through all the pages that are accessible to me within the user context that I'm running as. I make note of all the input vectors that potentially talk to the backend. I understand how the application functions. I try to figure out the logic of the application. I try to find subdomains in the application. I enumerate directories and pages that might not be directly visible to me through the application, and so on. And while I do all of that, I have my burp proxy listening silently and intercepting all the requests that I'm making to the application. So mapping the application is such an underrated step when it comes to pen testing applications, although I would argue it's probably the most important step. And the reason I say that is because I usually see beginners in this field get way too excited about the fact that they're testing an application, and then the first thing that they do is start throwing potentially malicious input vectors into the application to see if the application responds in an unusual way. And although this is a valid way of testing an application, it doesn't make you any different from an automated tool. So this is exactly what web application vulnerability scanners do. They crawl the application, they locate all the input vectors, and then they throw a ton of malicious payloads at these input vectors. And depending on how the application responds, the scanner logs the behavior as a potential vulnerability. And this way of testing usually only discovers the low-hanging vulnerabilities. So if you're doing exactly what a scanner can already do, then your testing is really not adding any value. Instead of doing that, what I would recommend is you leave that up to the scanners and instead spend quite a bit of time understanding how the application works, because most of the critical vulnerabilities found in applications are logic flaws that a scanner is not capable of finding on its own, or the vulnerabilities are embedded in pages that the scanner can't crawl, so technologies that the scanner can't crawl. Okay, so once you've mapped the application and you've listed all the input vectors that are potentially included in queries that are interacting with the SQL database, then it's a matter of fuzzing the application. And that's because we're looking for SQL injection vulnerabilities. You'd be fuzzing the application with SQL-specific characters. So what that means is you add special characters in the input vectors and see if the application responds in an unusual way. Now, depending on how the application responds, you start refining your query until you achieve your end goal. And that's what makes you different from a scanner, because a scanner just simply throws a bunch of input at the application. You as a human being you're capable of understanding the output of the SQL injection. And so you're able to refine your SQL injection using multiple requests until you actually achieve your goal. And we'll see how to do that in the exploitation section of this video. Okay, again, fuzzing the application means adding special characters and input vectors and seeing if the application responds in an unusual way. Now, that can be done in many ways. The first thing that I try to do is submit SQL-specific characters, such as the quote, or the double quote, or the hash, or the dashes that represent comments, and see if the application outputs an error. Now, errors are really important and really useful because they give you information about how the backend operates. So sometimes they give you the database that you're using, they give you the version of the database. We discussed that sometimes they actually give you the exact query. If they gave you the query, then you hit gold, because this way you don't have to develop your payload across multiple requests. Instead, you already know what the backend query is, and so you just develop your payload based on that query. And so the first thing that I do is try to output an error. Once I have an error, I try to build my query using multiple requests. So I refine my query based on the errors that I get, and I build my query. Now, in certain scenarios, you don't actually get an error, like for blind SQL injection. And so you also have to submit Boolean conditions, such as, and or 1 equals to 1 and 1 is equal to 2, and look for differences in the application's responses. So if you can get the application to respond differently when you force a true use case versus when you force a false use case, that means it's vulnerable to Boolean injection. Next, I do the same thing as Boolean injection. Instead, it would be to trigger time delays in the application and then see if there's a difference in the time it takes to respond. So if you input a function that causes a time delay and you actually observe that time delay, that means that the application is vulnerable to time-based SQL injection. Last but not least, I also submit out-of-band payloads that are designed to trigger a network interaction with a server that I control. And if I get that network interaction, whether it's a DNS lookup or it's done through HTTP, that means that the application is vulnerable to out-of-band SQL injection. And if I don't get them, that means it's not vulnerable to out-of-band SQL injection. So that's a high-level overview of my methodology when it comes to testing from a black box perspective. There's really 2 steps. First, mapping the application. So listing all the input vectors in the application, and then fuzzing the input vectors to see if I can find a SQL injection. And again, when it comes to fuzzing the input vectors, you can refine your requests based on the responses that the application gives you. Okay, next is white box testing perspective. So where you're given the source code of the application. In this case, the first thing that I do is I enable web server logging and I enable database logging. So enabling logging at the web server level will help because when you're fuzzing the application, like we did with black box perspective, it will generate errors on all the different invalid characters that you input into the application. And then that helps you to detect that SQL injection exists, and then also to refine your payload later on. Similarly, for database logging, I enable that because when I think that there's a SQL injection vulnerability and I enter a SQL injection payload in the parameter, I'd like to see how it was logged at the backend. And then depending on how it was logged at the backend, I can see what characters made it through and in what format they made it through. And then I could say, with maybe a 90% accuracy, that yes, this is vulnerable to SQL injection before I even look at the source code of the application. So once I have my logging enabled, the next thing that I do is map the application, just like I would with a black box perspective. So I'll start with the application's graphical user interface. I'll map all the visible functionality in the application, all the input vectors that potentially talk to the backend, and I'll make a list of them. Next, because I do have access to the source code, I'll also do a regex search on all instances in the code that talk to the database. And that really depends on how the application is programmed and then which database it uses and so on. But I would have regex strings that I look for in the code to see if I've missed anything that I haven't mapped from a black box perspective. And you'll see that there are certain pages that might not have been directly accessible through the main page of the application, and you didn't discover them through directory brute forcing. And so it's useful to actually look at the code and see if there's anything that you missed. Once I have a list of everything, what I would do is I would literally fuzz the application. So I would submit SQL characters that could potentially break the query. I will look at how they were logged using database logging that I enabled in the first step. And then based on that, I can usually tell if it's vulnerable to SQL code injection. And if I feel like it's vulnerable to SQL code injection, then I actually do a code review of that functionality. So for example, if I think the login page is vulnerable to SQL injection, what I would do is I will look for the login functionality, so the function that implements that in the code, and then I would do a walkthrough of that entire functionality from beginning to end, until I have confirmed that it is vulnerable to SQL injection in theory. And then to confirm in practice that it is vulnerable to SQL injection, then I would test it out. And depending on the response I get from the application, that means it's vulnerable to SQL injection. So again, that's my methodology. It doesn't mean that it's a methodology that you should follow. I do know people that would automatically just go into the source code and then do a search for insecure functions when it comes to parameterized queries and so on. And so if they find an insecure function, they'll start with that instead of doing kind of a hybrid approach of both black box and white box, which is the methodology that I described. Okay, in the past two sections, we talked about the different types of SQL injection vulnerabilities and how to test an application to see if it's vulnerable to SQL injection. Now, in this section, we'll talk about how to exploit SQL injection vulnerabilities in order to achieve your end goal. And that really depends on the SQL injection vulnerability that you're trying to exploit. We so far talked about five different types: error-based SQL injection, union-based SQL injection, Boolean-based blind SQL injection, time-based blind SQL injection, and out-of-band SQL injection. So in this section, we'll talk about how to exploit each one of these vulnerabilities. And we'll start off with error-based SQL injection. Now, as a reminder, we said error-based SQL injection is an in-band SQL injection technique that forces the database to generate an error, giving the attacker information upon which to refine a query. So successful exploitation of an error-based SQL injection is the fact that you can get the application to output an error. So there's really not much to exploiting this vulnerability. All you would do is submit SQL-specific characters, again, such as the single quote or the double quote, and you look for errors in the application. Now, different characters can give you different errors, so it's good to fuzz the application with the commonly known characters to generate errors. Next is union-based SQL injection. Exploiting this vulnerability is a little bit more involved. As a reminder, we said union-based SQL injection is an in-band SQL injection technique that leverages the union SQL operator to combine the results of two queries into a single result set. Now, in order for you to use the union operator, you have to follow the rules of the union operator, and there's two basic rules. The first one is that the number and the order of the columns must be the same in all queries. And the second one is that the data types must be compatible. So the query that the application is making and the query that you want to make have to satisfy these two rules. And so when you're exploiting union-based SQL injection, the first thing that you need to do is figure out the number of columns that the query is making. We'll talk about that in a bit, and we've got 2 ways of doing that. Next, you figure out the data types of the columns. We're mainly interested with string data because we want to extract things like usernames and passwords and so on. And so that's usually saved in string format. And so we need to find a data type that outputs string data. And this way we could output the data that we want to extract. And then once you've figured out the number of columns that the query is making and the data types of the columns, then you could use the union operator to output information from the database. Sometimes you don't actually get the data type that you want, and so it's a dead end. You can only extract, for example, integers or so on. So it depends on the SQL injection and the context that you're running with on whether you could actually exploit it to extract information from the backend database. Okay, so I said there's 2 different ways of determining the number of columns that are required in a SQL injection union attack. And one of the ways is using the order by clause. Now, this clause orders the result set of a query by a specified column list. So let's take an example. If you've got select the title and the cost from the product table where ID is equal to 1, and then you say order by 1, what that means is that you're ordering by the first column, which is by the title column over here. Now, the way to figure out the number of columns is to incrementally inject a series of order by clauses until you get an error or observe a different behavior in the application. So if I say order by 1, it'll order by the first column. If I say order by 2, it'll order by the second column. Now, if I say order by 3, that column doesn't exist. And so I get an error saying the order by position number 3 is out of range of the number of items in the select list. And so this way, I know that 3 is not a column. And since I incrementally increase the value of the order by integer over here, I know then the number of columns is this value minus 1. So 3 minus 1, which is 2. I know that number of columns that are being used in the SQL query is 2. So that's the way to do it using the order by clause. You could also figure out the number of columns required in a SQL injection using null values. So again, let's take example of a query that does select the title and the cost from the product table where ID is equal to 1. And then you say union, select null, and then dash dash for a comment character. Now, because a union using the union operator requires that this query has the same number of columns as this query, if you don't use the same number of columns, you will get an error. So if you incrementally inject a series of union select payloads specifying a different number of null values until you no longer get an error, then you could figure out the number of columns that are required by a SQL injection. So for example, when I put this payload over here, which is the one over here, it'll give me an error saying something like all queries combined using a union, intersect, or except operator must have an equal number of expressions in their target list. So it's telling me you're using the union operator, but your 2 queries don't have the same number of columns. And so I know that the query does not have only 1 column. So I increase the number of null values again by 1. So now I have 2 null values. And I try it out and I see if it gives me an error, that means it has more than 2 columns, and I try 3 and so on until I no longer get an error. Now, in this case, we only have 2 columns, and so this will output the results of this query over here and then the null values over here. So this won't give me an error, and that means that the number of columns that I have is equal to the number of null values that I entered, which is 2. So you could either do it by the order by clause or use by adding union select payloads specifying different numbers of null values. Okay, so that's how to find out the number of columns that the query is using. Next, we need to find a useful data type in these columns. And so the way to do that is to probe each column to test whether it can hold string data by submitting a series of union select payloads that place a string value into each column in turn. So over here, what I would do, now I know that it has 2 columns, right? From the previous exercise that we just did. So what I would do is I would add a string value, so A in the first column value, and see if it outputs an error. If it outputs an error saying that, I don't know, it's incompatible with a certain type, so in this case we're saying that the first value is actually integer, and so I get an error saying that it's incompatible, which means that the first column does not allow you to, is not a string data type. So next I try the second column over here. So I keep this as null and I try the second column, and if I get an error, that means this also does not accept string values. And I keep doing that until I find a value that allows me to enter string data. And again, in some cases, you might not actually find a value, and that's why some SQL injections allow you to do things like extract data from a database, whereas others, you're very limited in what you're, like the data type that you're allowed to extract. Okay, and so going back to the slide, explaining union-based SQL injection, we talked about how to figure out the number of columns that the query is making. We also talked about how to figure out the data types of the columns. If you have columns that are being outputted on the page and they use string data, then you could use the union operator to output information from the database. And that's how you exploit union-based SQL injection. Next, let's talk about exploiting Boolean-based blind SQL injection. So the first thing to do is submit a Boolean condition that evaluates to false and note the response. I've got an error here. It should say note. The next thing to do is submit a Boolean condition that evaluates to true. And again, note the response. If the response is different, or when you force a false statement versus a true statement, then you have a Boolean-based blind SQL injection. And the way to exploit that, we already talked about that, is to write a program that uses conditional statements to ask the database a series of true and false questions, and then monitor the responses. If the response is the same as the response you got when it evaluated to true, that means the question that you're asking the application is true. If the response is the same as the response that you got when you forced the false statements, that means the question that you're asking the application is false. And that's how you extract data from the database when it comes to Boolean-based blind SQL injection. Next is time-based blind SQL injection. What you do is you submit a payload that pauses the application for a specified period of time. If the application does actually pause for that specified period of time, that means it's vulnerable to time-based SQL injection. And then it's a matter of doing the same thing that you did for Boolean-based SQL injection. You just write a program that uses conditional statements to ask the database a series of true and false questions, and you monitor the response time. If there's a delay in the response time, that means the question you're asking the application is true. If there's no delay in the response time, that means the question you're asking the application is false. And then you send a bunch of those requests until you enumerate or you extract the thing that you want to extract from the database. And we'll gain experience in all of these different types of SQL injection vulnerabilities, like hands-on experience, in the next upcoming videos. Okay, so exploiting out-of-band SQL injection. Again, a reminder, this is a vulnerability that consists of triggering an out-of-band network connection to a system that you control. And the way to exploit it is to submit out-of-band payloads designed to trigger an out-of-band network interaction when executed within a SQL query, and monitor for any resulting interactions. So this is database specific, obviously, so knowing the type of database that you're using will be very useful in this scenario. And it depends on whether the database has these functions enabled. And so if you do get that network connection, if you receive that network connection, again, whether it's a DNS lookup or something else, that means that the application is vulnerable to out-of-band SQL injection. And in certain scenarios, you might be able to immediately exfil data from the application, so directly exfil data from the application, whereas in other cases, you're again stuck asking true and false questions, just like you would for line-based SQL injection. Okay, I didn't want to end this section without talking about automated exploitation tools. So one of the famous ones, and it's open source, is SQL Map. It's a tool that is used to find SQL injection vulnerabilities. It's very, very powerful, and it's very customizable in the sense that you select what parameters you could inject You also select the vigorosity of your testing. You also select the angle of your testing. So if it does find a SQL injection vulnerability, sometimes you have the ability to say, try to get a shell on the system, or try to dump the usernames and passwords of the applications on the system, and so on. And so this is a very important tool to look into when it comes to finding SQL injection vulnerabilities. Other tools that you could use, which are more for detection versus actually exploiting it to achieve your end goal, are web application vulnerability scanners. We talked quite a bit about these in this video. They're scanners that crawl the application and look for vulnerabilities. So not just SQL injection vulnerabilities, they look for all types of vulnerabilities in an application, and they usually report it as a vulnerability. They don't actually go all the way to exploiting it to get a shell on the system or to dump usernames and passwords. And some of these tools are open source, whereas others are paid. So something to look into. Of course, these tools have limitations. And maybe I'll do a video specific on that because that's what my research was on. But these tools have limitations, and they operate from a black box perspective. So there are other tools that operate from a white box perspective. They're called static analysis tools, whereas these are called dynamic analysis tools. So something to look into when you want to automate a portion of your web application testing. All right, now that you know what a SQL injection vulnerability is, how to find it, and how to exploit it, the next thing to learn is how to prevent SQL injection vulnerabilities. And that will come in really handy when you're writing pen testing reports and you need to provide recommendations to your client on how to remediate the vulnerabilities that you discovered. So there are the primary defenses and the additional defenses, which use the concept of defense in depth. We'll talk about each defense in the next couple of slides, and those are the ones that are mentioned in the Web Application Hackers Handbook. But the idea is I have this highlighted over here because this is the correct way of preventing SQL injection vulnerabilities, and that is by using prepared statements or parameterized queries instead of string concatenation within a query. All the other options are partial options and should be used only as a last resort with the knowledge that they might be bypassed or they might be implemented incorrectly, and they might cause a SQL injection in the future. And so let's talk about each one in order, starting with the correct way of defending against SQL injection vulnerabilities, and that's using prepared statements. Okay, so let's take an example first. So you've got a code block over here. The first one, which is query over here, has select the account balance from the user data table, where username is equal to request.getParameter customer name. So what this does is it takes user input, so user controlled input customer name, and it adds it directly to the query, and then it defines the structure. So it's defining the structure of the query, and then it executes the query. So do you spot the issue over here? It's a bit obvious. The user supplied input customer name over here is embedded directly into the SQL statement. And so anything that the user adds over here might actually be interpreted as part of the query. Okay, so using prepared statements can prevent SQL injection attacks, and that's because the construction of the SQL statement is performed in two steps. The first being the application specifies the query structure with placeholders for each user supplied input, and then the application specifies the content of each placeholder. This way, there's no way that a user supplied input that is specified in this step over here can ever interfere with the structure of the query in this first step. And that's because the query structure had already been defined, and now any placeholder data is interpreted in a safe way as literally data versus SQL code. And so let's take an example of code that is not vulnerable. So in this code over here, you could see there is the variable cust name. It takes an user supplied input, customer name. You've got the query over here being defined. And then over here, it prepares the statement through a database connection. So the prepare statement method is invoked to interpret this query and fix the structure of the query. And then the setString method is used to specify the parameter's actual value. Now, because the query structure has already been fixed in the prepared statement, this value can contain any data without affecting the structure of the query because it will literally be interpreted as data versus as part of the query. So if the user over here had put in SQL characters like a quote or a double quote or so on, that will be interpreted as data, and it can't ever change the structure of the query because the structure has already been determined and fixed. And that's how you prevent SQL injection vulnerabilities. That's the correct way of preventing SQL injection vulnerabilities. Now, there are partial options that the book talks about. One is the use of stored procedures. So stored procedures are batches of statements grouped as a logical unit and stored in a database. This is not always a safe way of preventing SQL injection vulnerabilities because if it's implemented incorrectly, it could still be vulnerable to SQL injection. So it still needs to be called in a parameterized way in order for it to be safe against SQL injection vulnerabilities. The reason that some people would use stored procedures or any of the partial options is because there are certain parameters that you can't specify as placeholders in parameterized queries. And for example, the table name or the column name. And so if that's user controllable, you have to use one of the partial options in order to prevent SQL injection attacks. Now, the correct way of doing it is that this should never be user controllable, but if it has to be user controllable, then you use one of the partial options. That's option 2. Option number 3 is whitelist input validation. So define which values are authorized. Everything else is considered to be unauthorized. And we talked about parameters that can be placeholders like the table name and the column name. In this case, a whitelist input validation would be you know exactly the column name should be or the table name should be users. And so you only accept the value users and nothing else. And this way you prevent the attacker from injecting other characters or other strings that could potentially interfere with your query. Option number 4 is escape all user input. So validate user input, and that should only be used as a last resort. Again, it's a partial option versus something that for sure prevents SQL injection vulnerabilities. Okay, additional defenses. Before we talk about that, let's talk about the concept of defense in depth. So the idea is to make it as difficult as possible for the attacker to compromise your organization. And that's done by providing additional protection in the event that the frontline defenses fail. So if me as an attacker, I want to gain access to your organization, and I manage to get past the first block that you had put in my way, then I would have 2 other obstacles that I need to get through before I get to your organization. And so in the same sense, although you use parameterized queries, just in case you by chance forgot to include it on one parameter in one page, you want to have defenses in place that if a SQL injection vulnerability was exploited, the attacker gets another obstacle in their way before they could achieve their goal. And so one is least privilege. So the application should use the lowest possible of privileges when accessing the database. And the reason behind that is if SQL injection exists in your application and an attacker exploits it to gain remote code execution on the server that the database is installed on, then the attacker will gain the same level of privilege that the database is running with. And so if the database is running as system or root, then the attacker already has all the privileges that the attacker needs on that server. However, if it was running with a service account that has all the privileges stripped, then the attacker has to find ways to escalate privileges on the server before they can, for example, move laterally within the organization. And so the application should always use the lowest possible level of privilege when accessing the database. Any unnecessary default functionality in the database should be removed or disabled. That includes things like functions that allow you to execute system commands from the database, also functions that allow you to make a network connection that we talked about out of band SQL injection, right? So functions that allow you to do that. So any unnecessary default functionality that you don't need for the application to function, that should be removed because it decreases the amount of things that an attacker can use in order to penetrate your organization. Ensure CIS benchmarks for the database in use is applied. So there are benchmarks for most of the databases out there. And these are rules on the way to configure your database in order to ensure that it's secure. And it includes things like the application should use the lowest possible level of privilege and removing any default functionality and so on. So look up your database version and you should be able to find a CIS benchmark for it. And last but not least, this one's obvious, all vendor-issued security patches should be applied in a timely fashion. So if you get notified that the database version that you're using is vulnerable to some kind of vulnerability, then you should patch your database as soon as possible to decrease the window of time that the attacker has to attack your database and to exploit the vulnerability. And then this one, we already discussed it. So whitelist input validation. So although you have parameterized queries, an additional defense, so a defense in depth, is to still whitelist all the input values that come from the user, so come from the client side. Okay, and that wraps up the last section. Before I close this video, let's talk about the resources that were used to create this video. One is the Web Security Academy, so the SQL injection module, and that's the module that we'll be following for the next couple of videos. Next is the Web Application Hackers Handbook, so Chapter 9, Attacking Data Stores. If you want to learn more about this topic, you should go and read this chapter. And then we've got the OWASP Guide for SQL Injection and SQL Injection Prevention Cheat Sheet. I also included the Pentest Monkey URL. And the reason behind that is because it lists all the different SQL injection payloads that you could use depending on the database that you're using. And then there's other ones like payload all the things and so on. We'll see a lot of this when it comes to the videos. To wrap up, in this video, we learned about SQL injection vulnerabilities, how to find them, how to exploit them, and how to prevent them. You can find a link to the slides in the description. In the next couple of videos, we will gain hands-on experience exploiting all the different types of SQL injection vulnerabilities that we learned about in this video. If you made it this far, thank you for watching. Make sure to hit the subscribe button and share the video so that it reaches a wider audience. Also comment below what you liked about the video and the type of videos you would like to see in the future. Thank you and see you in the next video.